Okay, folks, we can get going. So before I get back into the content for today, which I'll just remind you is building up some understanding of PIO so that we can talk about the VGA driver. And I want to just continue that story a little bit further today. But before I do that, there are a couple of common bugs that I've noticed in labs so far this week that I want to just talk quickly about. The first is, as part of your checkoff this week, you're required to integrate a potentiometer with the analog to digital converter. There does, in fact, exist a ADC example in the course demo code, and indeed we talked through it in lecture, but it's a rather complicated one that uses a DMA interface to the ADC. So I just wanted to draw your attention to in that Pico examples repository that we've been using as the basis for our conversation about PIO. If you go to this ADC folder, the simplest example in here is called Hello ADC. And this shows the minimal setup for the ADC. Why is that screen too big? Let me see if I can fix that. Full screen. That's better. This shows the minimum setup for the ADC that you'll be using in lab this week. So all that I want to just point out is when we talked through that ADC demo last time, I showed that there was a bunch of FIFO configuration and DMA configuration and so forth. In your case, for this lab, all that you need do is call ADC init in main. I'll just remind you that this starts up the ADC peripheral. Among other things, one of the things that it does is start the clock associated with the ADC. The ADC has its own 48 megahertz clock. That clock's it's part of a phase lock loop, and that takes a little bit of time to stabilize. And so you call ADC init, and it sets all that stuff up and blocks until everything's stable and ready to go. You call ADC GPIO init, with the argument being the GPIO into which you're going to plug, in your case, the potentiometer. So you have a few choices here with regard to which GPIO you're going to choose. Remember that there's a 5-way mux into the ADC, and on the Pico board, 3 of those inputs to that 5-way mux go out to GPIO pins. One of the missing ones goes to an internal temperature sensor. The other one on the Pico goes up to vSense. So you have 3 to choose from. ADC mux input 0 is on GPIO 26. When we call this, it configures the pad associated with that GPIO for analog input. Turn off all the digital stuff, get it ready for analog input. And then the last thing that you'll call is ADC select input, in which you tell the ADC peripheral which of those mux inputs you'd like to listen to. And in your case in this lab, you only need to read one. You're only going to have one potentiometer plugged into one of the ADC mux inputs. It just has to be, whichever one you choose, it has to be the one associated with the GPIO you've selected. Mux input 0 happens to map to GPIO 26, but you do have 2 other options if you care to change that. You could, if you wanted to, as we talked about, set this up in round robin mode so that you sample a bunch of different mux inputs sequentially, but you won't be doing that in this lab. And once you have that set up, for purposes of lab 2, the ADC is ready to go. And every time you want to gather a sample off the ADC, you simply call ADC read, and that will give you back an unsigned 16-bit short, a UART 16. It's going to be some number in the range of 0 to 2 to the 12th, because this is a 12-bit DAC, or a 12-bit ADC rather, right? So you'll get some number in the range of 0 up to 4097. Now, by the way, one of the things that some of you have noticed is if you are just reading the ADC and using the value that you read to, say, set the number of balls in your Galton board, some of you have noticed that even when you're not moving the potentiometer, that number's fluttering a little bit. And that's sort of expected because remember when we talked about the ADC, one of the things that we discussed was though this is a 12-bit analog to digital converter, your effective number of bits is 8.7. So what that suggests is that the bottom 3 to 4 bits are very, very noisy. And so even when the voltage coming into the analog input is not changing, you're going to see some noise in the least significant 3 or 4 bits of that ADC. So how do you handle this? Well, you have a couple of options. One option I would say is you could call ADC read, and before you use the result to, say, set the number of balls in the Galton board, shift out the least significant 4 bits. That decreases your effective range, right? Basically now what we're saying is instead of getting 12 bits of resolution for our ADC, we're getting 8 bits of resolution. So instead of numbers up to 4096, we get numbers up to whatever that is, 256, if I'm doing my powers of 2 right. But you'll get much less noise. Or alternatively, and I think a little bit more elegantly, if you go to the course web page, there's a page here on digital low-pass filters. Oops, wrong click. There's some math here to explain why this works, but of relevance to you all is with one extra line of code, you can implement a very quick and dirty but very effective low-pass filter on your analog input, so that you get to specify the maximum rate at which ADC values, filtered ADC values, are allowed to change. So this web page was written for a motor control lab, which is why the variable names here are sort of suggestives of motor control. But in your case, motor display here would be your filtered ADC output, right? So that you might call that variable something like ADC underscore filtered or something. And PWM on time in this line of code would be your raw ADC values. So what this says is every time you go to read the ADC, rather than using that value directly, what you would do is you'd have some initial value for your filtered output. Maybe it's 0 or maybe it's halfway or something. And you'd say, rather than using this directly, what I'm going to do instead is plug it into this equation, which will low pass this, and I'll use the output of the low pass filter. And if you're squinting at that and trying to figure out how the hell is that a low pass filter, you can derive exactly this expression from the equation for just an RC low pass filter. You can show that the two are in fact equivalent. And by adjusting the amount by which you shift here, you adjust the cutoff frequency of your low pass filter. So you might consider doing this if you're seeing a little more noise than you would like on your ADC input. Are there questions about that? Okay, another common bug that I've seen is I've seen a number of groups with physics that looks great, but they drop a ball on the top of the Galton board and it bounces directly on top of the board for a very, very long time, and then either sits there forever or maybe slowly leaks through the top board. More often than not, what you're observing is sort of what should happen in the event that your x velocity for your ball is exactly 0. And so often what this suggests is that you have some error in your randomization of the initial x velocity. Remember, your balls are supposed to drop with random initial x velocities. So I thought we'd take just a moment to talk about that. And so let's suppose we want a random Vx in the range of -1 to 1 in fixed point. So how would we do that? Well, we could say Vx is going to be equal to, and then the exercise here is going to be, we're going to use rand to generate a bunch of random bits, and then we're going to play with masks and shifts to put those bits wherever we need for them to be for this fixed point representation that we've chosen. And I'll just remind you that in this lab, we happen to be using a fixed point representation that has 16 integer bits and 15 fractional bits. So there's 15 bits below the decimal and there's 16 bits above the decimal. And so if we were to just call rand, what this does is give us 32 random 1s and 0s, which is actually a little bit different than I have on the fixed point web page. I wrote that fixed point web page when this class was being taught on the PIC32, and as it turns out on the PIC32, rand would give you 16 random bits. On the RP2040, the way to figure this out, incidentally, is the SDK has a parameter called rand max, which specifies the maximum value that you'll get out of rand, and you can go find that in the SDK and learn what's the maximum random number that we're getting out of rand. In any case, this one turns out to be giving us 32 random bits, but that's fine. So when we call this, first of all, just that gives us a whole bunch of random bits. If we were to then mask that with, say, 4 Fs, the consequence of this is we retain 16 random ones and zeros in the least significant 16 bits. And by masking out the rest of them are 0. And so after having done this, we have 32 random bits, and then we mask it, and now we have kept the 16 least significant ones, and the rest have become 0. So in our fixed point representation that we've chosen, in which we have 15 fractional bits and 16 integer bits, that number, interpreted as a fixed point value, is going to be a random number in the range of 0 to 2. Does that make sense? Because the lowest number that we could possibly get there is all zeros. The biggest number that we could possibly get is 16 ones. So that would be a single 1 on the integer side of the decimal, and then all the fractionals ones, which is a number very, very close to 2. So that's a random number in the range of 0 to 2. Let's say we want a random number in the range of -1 to 1. We could subtract off 1 represented as fixed point. So if you do this, what you'll end up with is a random x velocity correctly represented in fixed point in the range of -1 to 1, which is about the right range for the distance that we're dropping these balls onto these Galton boards. Does that make sense? Yes?
Wouldn't there still be a 0?
Yeah, absolutely. It's going to be extremely rare. So you're making the correct observation that this, I introduced this because we were seeing this bug where balls are dropping directly onto the board, and you're making the good point that that's still a possibility here. We could still get zeros. It is happening on occasion, on very frequent occasion. And so the bug that I am seeing is that students are accidentally generating random VXs that have no fractional parts. The random number is either -1, 0, or 1, so that basically every third ball just bounces off the top of the Galton board. But you're absolutely correct that here, every very large number of balls will bounce directly off the top of the board. If you wanted to address that bug, one way that you could do it is the first time you encounter a new peg, you generate a sound. You could also inject a little bit of randomness in your x velocity every time you bounce, which would also be very physical, right? You bounce off a little imperfection and it bounces a little bit one way or another way. So you could inject a little bit of randomness at the collision events, and that would probably address that. Though I think you'll find that if you use this, it'd be very interesting to measure the frequency with which you see that, but it's going to be very rare. What if we wanted a random number between -2 and 2? How do we change this? Yes? Could you multiply the output by 2? Well, you could, yeah. Or add it to itself, yes. Or you could say, instead of keeping 16 bits, I'm going to keep 17 bits. So instead of FFFF, 16 ones there, I'm going to have 17 ones. So now I've kept the least significant 17 random ones and zeros. The stuff inside of that parentheses now will give me in fixed point a random number not between 0 and 2, but between 0 and 4, because I have one extra bit there. And then I could subtract off into fix of 2. Make sense? So the game that we're playing, like I keep saying, is we're keeping in mind where our decimal point lives in our chosen fixed point representation. We're using rand to just generate a bunch of random ones and zeros, and then masking and subtracting to put those random zeros those random ones and zeros where they need to be for our value. Yeah.
So that's more than 60 bits. That the least significant bit is just discarded.
Can you repeat the question? What's the question?
So I might be wrong, but
Yeah.
I think by 1 FFFF would lead to an output of 17 bits.
Yes.
Does that mean the least significant bit is just somehow discarded in the conversion to fixed point?
Yeah, yeah. Thanks, Bruce. Any other questions about this? Any other bugs that people are encountering? Yes?
So in the case where, or I guess we're observing a lot of collisions
So it bounces off of one row and bounces off the one above it again?
Yeah.
That's okay. Yeah, yeah. So you could mitigate that by decreasing your bounciness parameter, and it would lose more energy upon each collision. Yes?
Ours just freezes when it hits the peg, like every once in a while.
Freezes when it hits the peg every once in a while. That I'll have to look at the code. I'm not sure. The other thing I just wanted to mention, let me just do this briefly. I have seen a number of bugs associated with using the DMA to generate the sound effects. And there are sort of two approaches that you could take to do this. I'll remind you that let me just stop sharing here for a minute so that the camera's bigger. I will remind you that the demo code has two DMA channels. You have the control channel, and you have what we call the data channel. The control channel is rewriting the read address of the data channel, because the DMA channels on the RP2040, if you point the data channel to the beginning of the array that we want to send out to the DAC, and you say, please do as many transactions as there are elements in this array, it'll say, okay, sure. It'll start at the beginning and walk to the end of the array. And if you don't set its read address back to the beginning of that array and you trigger it again, it'll just walk right off the end of the array and keep going through memory. And you'll be sending something out to the DAC, but it's not going to be a sine wave. It's going to be whatever happens to be in memory after your sine table array. And so the demo wow, this chalk sucks. Let's see. The demo chains these two. So the control channel rewrites the read address of the data channel and triggers it, starts it. The data channel produces a whole sine wave, goes through the full table, and then triggers the control channel to start again. And they ping pong back and forth forever, which is why in the demo, what you hear coming out of the speakers is a persistent sine wave. You get one period, re-trigger, another period, re-trigger, and it's persistent. We don't want a persistent sine wave. We want a single period of a sine wave every time a ball strikes a peg. So how could we do this? You have two approaches. One approach is you delete the chain from the data channel back to the control channel. So you keep the chain in this direction so that every time you start the control channel, it rewrites the read address of the data channel and starts it. The data channel will put out one sine wave, but then it won't trigger back to the control channel. And you won't hear another sound come out until in your software, you re-trigger the control channel. And re-triggering the control channel will rewrite the read address of the data channel and trigger it, and you'll hear another sine wave come out. The alternative would be to get rid of the control channel altogether, only have the data channel, and every time you want for a sound effect to occur, you first rewrite the read address of the data channel to point to the beginning of that array, and then you trigger it. And as it turns out, this is getting perhaps just slightly into the weeds, but I think it's instructive to look at. You could do that in sort of two subsequent actions in the SDK. There's a function that allows for you to rewrite the read address of a particular DMA channel, and then one that will allow for you to start it. You will also notice, I'll just point out, that every one of these DMA channels, we'll just look at channel 0 for instance, have registers associated with the read address, the write address, the transfer count, control and status, etc. And then all those registers are repeated with these little AL1s injected into the names. Those AL1s stand for alias. And if you were to write to, say, the AL1 read address for the channel that you want to trigger, the consequence of writing to these registers as opposed to those registers is when you write to this, you also trigger the channel to start. And so you could delete the control channel altogether, write specifically to the read address alias trigger register of the data channel, and the consequence would be that you would reset the read address of the data channel and it would start. Yes?
Is there any reason why we can't delete
If you delete the other chain, no, that would be fine. That would be fine. So as long as, to start, this is set to the correct read address, then if you delete this chain, this chain, and keep this one, then the first time you trigger it, data will send out the sine wave, trigger the control channel, which rewrites its read address but doesn't start it, and then the next time you start the data channel, it would be properly configured. That would be fine as well. Questions about that? Is the advantage of the ADC channel in the context of this lab clear? We're using the ADC channel in this lab to produce sound. I'm sorry, DMA channel. I'm misspeaking. Is the advantage of the DMA channels in this lab clear? So let me just remind you that in lab 1, we also produced sound. We were also producing sine waves. We were using it, we did that via a very different mechanism. In lab 1, we were using a timer interrupt and the direct digital synthesis algorithm to produce sound. That has the advantage that we can build a synth. We can dynamically at runtime change the sounds that we're generating because they can be functions of some equation that we're evaluating in our code. We're not doing that here. We're producing a single sound, but the advantage of this is we're spending 0 CPU time to produce this sound effect. When you triggered this DMA channel, either one of these, depending how you have the chains hooked up or whatever, but when you trigger that SDK function call that you will call in order to start the DMA channel is non-blocking. You hit that and you carry on. And once you hit that, in the background, totally separate from the CPU, a little thunk will come out of the speaker. Because you want to spend, in this lab, all your CPU time on animation, you want to waste exactly 0 on audio synthesis, we can offload in this lab all of audio synthesis to these DMA channels. So that's why this makes sense in the context of this lab. Other thoughts about this? Questions? Yes?
So in the channel, in this case, you used to send data to the DAC that produces audio. You can send data to any peripheral the same way?
Any peripheral you want. So yes, and more specifically, the DMA channel in this lab is being sent to move data from memory to a particular register associated with the SPI peripheral. And then the SPI peripheral is configured such that anything that lands in that register gets whisked away across the channel. But yes, on this microcontroller and on essentially any microcontroller, the power of these DMA channels is that you can point them to any memory address that you want to, and all these peripherals that we're talking about, the SPI channels, the I2C channels, the PWM channels, everything on here is memory mapped. The configuration registers for all of them have addresses that we can go look up. And so, yes, you could use these DMA channels to communicate from memory to any of those other peripherals. You could use them to communicate from one peripheral to another peripheral. You could use them to communicate from a peripheral to memory, from the ADC to memory, for instance. And all of that data communication occurs as a background process. You can have a huge amount of data moving, right? Because every one of these channels can move a 32-bit word per cycle. Huge amount of data can be moving in the background. Okay, any other thoughts about this? We'll see another example of the utility of DMA when we get to the VGA drivers implementation. That makes extensive use of them. So let's just finish the PIO story so that we can get to that ideally next time. And I will just remind you that the strategy by which we've been talking about these PIOs, because they're a little bit unusual, the strategy that we've been taking is to look at PIO implementations of friendly old familiar protocols, UART, and we're going to look today at SPI. And once we see what a PIO version of these friendly familiar things looks like, we'll look at the PIO implementation of something that's perhaps a little bit less familiar, which is the VGA standard. So last time, we talked through this hello PWM example. somewhere, or hello PIO example. Sorry, I keep misspeaking today. And I'll just remind you that all this did was we could dump something into the FIFO, it would appear on a pin. And then we started looking at the UART transmit. And I won't talk through this in detail. I'll just very briefly remind you what was happening here. Remember that the UART protocol, if I want to transmit something over UART to a receiver, my transmit pin idles high at high voltage. And then when I'm ready to send something, I send a start bit. So I pull that pin down for 1 bit time. And then I put out 1 bit per bit time across, over that channel, high, low, high, low, high, low. And I terminate my transaction with a stop bit, pull it high for 1 bit time. And that's precisely what this PIO state machine is implementing. We have a pull instruction to grab an 8-bit character from the TX FIFO. In the event that there is not something in the FIFO, as we talked about last time, this stalls and just waits for something to appear. And then simultaneously with that pull instruction, we're using the side set to say, please put the side set pin high. And we have that configured such that that is our transmit line. So we're saying, please idle high until something appears in the TX FIFO. Once something does appear, okay, pull it, move it into the output shift register. And then we call set X7, set the X scratch register's value to 7, and simultaneously, please put the side set pin low, and wait for 7 additional PIO cycles. Right there is our start bit. Pull low, wait for 8 PIO times, which is 1 bit time as we have this configured. So there's our start bit. And we've used the time that we have available during that start bit to initialize our X scratch register that we're going to use to count each bit that we send out over the transmit line. We then call out pins 1. That means please move 1 bit from the output shift register to the pins. Shift it out of the output shift register to the pins. So that will toggle that output pin, which happens to be mapped to the same GPIO. So right, this is toggling our TX line. And then we hit a conditional jump. Please evaluate the X scratch register. In the event that the X scratch register is non-zero, jump back up and put another bit out. And also, when you do that, decrement the X scratch register. But before you jump, wait for an additional 6 PIO cycles. So if you count this, we put out a pin. That instruction takes 1 cycle time, 1 PIO instruction time. We wait for an additional 6, so that by the time we get back up there, we are 8 PIO instruction times later. So we're getting exactly 1 bit every 8 PIO instruction times. We spin here 8 times, clocking out those bits, and then we jump back up to the top, sit on that pull instruction while also putting out a side instruction. The additional 7 delay there is in the event that we got there and the user's already put something in the TX FIFO for us to send our next transaction. We still have to hold that transmit line high for the stop bit time, and that enforces that we do that before we send the next start bit. Okay? So in brief, that's what we talked about. And I thought it would be interesting to just very quickly look at the UART receive state machine. And as this example includes a couple of different demos. One that is sort of the minimum viable version, which we'll talk about. And then I'll also just point out that down here there's a slightly fancier version that keeps an eye out for things like framing errors or break conditions or so forth, and lets the CPU know that something like that has happened. But let's just focus for the moment on the minimum viable version. So this is a UART receiver, right? So this is looking at the UART pin and waiting for data to appear there. It knows that data is going to start appearing there when it sees a start bit, when it sees that pin go low for 1 bit time. So our first instruction here is not a pull. It is instead a wait 0 pin 0. What this is saying is, please wait for a logical condition on 0 on pin 0. And we will have mapped which pin we're talking about down here. We might have multiple pins up there. So pin 0 is, of course, our RX line. We've configured it such that it's the RX line. So we'll stall on this instruction for as long as our RX line stays high. The moment it drops low, we pass through that. We set the X scratch register to 7 and wait for 10 bit times. We have to wait for 10 bit times because we're waiting through the duration of that start bit until we get to about halfway through the first data bit. And that's where we want to sample the data that's actually on the RX line. We're trying not to sample it right at the edges where it's changing. We're trying to sample it instead in sort of the middle of the bit. So that gets us to the middle of the bit. We do in pins 1. That means please move 1 bit from the pins, and I will have told you which pin I'm talking about, to the input shift register, and then do a conditional jump. In the event that x is non-zero prior to a decrement, jump back up and pull another pin in after you've waited for a bit time. Okay? Once you've counted off having received 8 bits, jump back up and wait for the next transaction to occur. So it looks very similar, except instead of outs, we have ins, because we're sucking data in from a GPIO instead of putting it out to a GPIO. But this looks nearly identical. The only difference up there is that rather than waiting for 1 bit time, we're waiting for 1.5 bit times initially to get ourselves to the right phase, right, with the incoming data. And then rather than stalling on a pull, we stall on a wait. We're waiting for somebody else asynchronously to send us a transaction. Okay, now before I talk about VGA, I want to look at just one more familiar protocol, which is SPI. We spent a bunch of time talking about SPI, so you guys are like SPI experts. Well, let me just remind you. Let me just briefly remind you that an SPI channel includes, there are 4 wires connecting the main device to the secondary device. There's a clock line, a MOSI line, and a MISO line. Main out, secondary in, main in, secondary out. So that's for data going this way and data going this way. And then there's a chip select line connected to each of the peripheral devices. And then the way that data is actually communicated between a main device and a secondary device is each has a shift register. In the picture here, it happens to be 8 bits wide, but on the DAC, it's actually a 16-bit wide shift register. The RP2040 in our case has one. The DAC, for instance, has its own. When we want to send something to the DAC, we drop chip select, pull it low. That tells the DAC I'm about to send you something. And then we start clocking out highs and lows on the clock line, and synchronously with the rising edges or falling edges, depending on the particular mode of that particular SPI channel, we change the data on the MOSI line, and the device that we're communicating with will change the data on the MISO line, so that over the course of, in this case, 8 clock cycles, we replace the data in this shift register with the data that was here, and we replace the data that was here with the data that was here. Now, some of you made the observation that the DAC doesn't actually have a main in, secondary out line because we don't actually get anything back from the DAC. Okay, but in general, this is how these transactions occur. And the timing diagram would look something like the following. For an 8-bit transaction, we drop chip select, start clocking out the clock lines, and then in this picture, the data is valid, it's stable on the rising edges of the clock, and then it changes on the falling edges of the clock. But like we talked about a handful of lectures ago, there's a couple of degrees of freedom here, and you have to read the data sheet to learn the particular mode for the device that you're communicating with. So you could imagine, you know, 1 degree of freedom is, does our clock line idle low and then pulse high, or does it idle high and pulse low? That would be the polarity configuration. You have 2 options there. And then the data, is the data stable on the rising edges and changing on the falling edges, or the opposite? Does the data change on the rising edges and is it stable on the falling edges? Okay, so there's 4 modes. The DAC uses mode 00, which is this picture actually. The clock is idle low, active high. Data is stable on the rising edges, changing on the falling edges. So our PIO implementation of this is going to be manipulating the clock line, the MISO line, and the MOSI line. And it assumes that the chip select line is being manipulated in software by a GPIO put instruction. Though as we'll see, they do include some examples of PIOs that do automatic chip select toggling as well. So let's look at the SPI PIO. Look at this. It is only 2 instructions. Okay, so like I said, there's a few examples here with sort of increasing fanciness. It adds a chip select line or it changes the polarity or so forth. But let's just look at the bare bones example. Okay, bare bones example starts here. SPI, clock, phase, and polarity 0. And we're saying we're going to have one side set pin. This program starts on an out instruction. Out pins 1 means please move 1 bit from the output shift register to the pins. Oh, and when you do that, please toggle the side set pin low and stall for 1 instruction. So we plunk some information into the TX FIFO, right? This is stalling on that out instruction until something has appeared in the TX FIFO. We plunk something in. As we'll see in a moment, this particular example has auto pull enabled. That's why you don't see a pull instruction here. Plunk something in. We move 1 bit to the pins and simultaneously toggle our side set pin 0. So in this line, the out pin is our MOSI line, our main out secondary in line. This would be, for instance, one of the bits being sent to the DAC from the RP2040. The side set pin here is the clock. And so what this is allowing for us to do is change the data on the MOSI line simultaneously with toggling our clock low, which is exactly what the timing diagram calls for. And then we wait for one PIO instruction time. We then call in pins 1. We will have a different pin mapped to the in instruction. So the in instruction will be talking to one of the GPIOs. The out instruction talks to another GPIO. So the out instruction is talking to our MOSI line, our main out, secondary in. The in instruction is listening on the MISO line, the main in, secondary out. We pull 1 bit off our input pins and simultaneously toggle the clock from low to high. This example, if we scroll down here just a little bit, this example, sorry, I'm a little lost. This example has both auto push and auto pull enabled. And so you'll notice, for instance, ultimately we want to take the data that we're receiving over the MISO line and give it back to the ARM to do something with. But there's no push instruction here. No instruction that takes the data from the input shift register and moves it over to the RX FIFO. We could scroll down here and look at the configurations, and what we would find is we've set up that auto push feature so that the shift counter is counting the number of bits that we have moved into the input shift register. Every time it counts up to some threshold, perhaps 8, perhaps 16, it automatically does a push. Likewise, the output shift counter is counting the number of bits we've shifted out to the pins. Every time it counts up to some threshold, in the case of the DAC, this would be 16 because we're doing 16-bit transactions, it automatically executes a subsequent pull. And in the event that there's no data to pull, it'll stall on that out instruction. And so auto push and auto pull in this example has saved us 2 whole instructions. But that whole protocol in PIO reduces to a 2-line program. So what this means is you got 2 SPI peripherals on the RP2040. If you need a third, build a third. If you need a fourth, build another one and another one and another one, right? You could build a whole bunch of SPI channels. Build a whole bunch of UART channels. We could look at I2C implementations here. Build a whole bunch of new I2C channels. Or, as we'll discuss, you could build, if you're trying to communicate to something strange that's sort of non-standard, you could build yourself a non-standard interface. VGA is going to be one of these non-standard interfaces. Are there any questions about this? I want to just state that this is, because this is a unique peripheral, it is not clear how best to teach this peripheral. And so I'm doing this in a way that I think is the right way to go about it, but I'm not certain of that because there aren't a bunch of like resources that I might draw upon to see how do people generally get introduced to PIO. So the thought here, I'll just remind you, is we looked at a very simple example. Now we're looking at examples of familiar protocols to build up some intuitions for looking at an example of a non-familiar protocol. Yes?
So do push and pull just take so little time that you can sort of add it to any instruction and you don't have to worry about timing?
Yes. So that's a great question. So if we have auto push enabled or auto pull enabled, it will do that in one instruction or one clock cycle. So the auto push and auto pull, in other words, will keep up with your PIO program, even if your PIO program is running at full clock rate. Again, it's kind of astounding. This is guaranteed single cycle instruction. So in one clock cycle, 125 megahertz, 250 megahertz if you've overclocked it, you're grabbing a value off the pin, setting another pin, stalling, and possibly also doing a push, moving data from an input shift register out to a FIFO to be consumed by a DMA channel, for instance. What time is it? 8 minutes to go. Okay, so hopefully with some intuition built up for how these PIOs work, what the programs for them look like, and how we kind of interact with them. We've not yet, by the way, seen an example of a DMA channel interacting with the PIOs, but I'm going to use the VGA driver to speak to that. Okay. So with all of that, I'd like to next talk about the VGA implementation, the PIO implementation of the VGA standard that you're all using, which will allow for us to have an informed conversation about how you can modify it, either to overclock the RP2040 or to drop from 4-bit color to 1-bit color to buy yourself some memory if you become memory constrained instead of time constrained. So I'm not going to get all the way into that today, but maybe what I can do is we started this whole conversation about PIOs. We motivated it by looking at the PIO standard and having a conversation about how, yeah, we could probably get this to work without a PIO coprocessor, but man, it would probably take a lot of CPU time. So let me just remind you, the standard that we will be implementing with PIO controls 5 GPIOs, well, 6 GPIOs. It controls H-sync and V-sync, which gives timing information to our VGA about when to move to a new line or when to move to a new frame. It controls one channel for red, the red input to the VGA, another one for blue, and 2 for green. We spend the extra bit on green because we have the most sensitivity on green. Okay. Let me just remind you that the way that the timing works here is our H-sync timing line stays high the whole way across a row of the VGA screen, right? So if we want to start writing to the VGA screen, H-sync is high, and then at 25 megahertz, 25.172 megahertz technically, but the RP2040s are driving this at 25 megahertz, we change the voltages on the RG and B data lines all the way across the screen 640 times, and the VGA screen is looking at the voltages on those RG and B inputs as it moves across the screen 25 million times a second, and using those voltages to set the colors of each of these pixels. We get to the end of a particular row, the H-sync line remains high for a certain number of cycles, 16 as it turns out, sinks low for 96 clock cycles, and then goes high again for 48 clock cycles, after which the VGA knows, okay, I'm going to be looking for the voltages on the RG and B inputs again, and I'm going to use those to set the values on the second row of pixels. And then the same thing happens. We do the third row, fourth row, etc., all the way down, all 480 rows. And then when we get to the bottom, H-sync keeps ticking away as usual, but in these blanking regions, we're holding RG and B low, and our vertical sync indicator will remain high. It's been high this whole time. It remains high for an additional 10 line times, syncs low for 2 line times, high for an additional 33. By the way, the terminology used for how many cycles are before the pulse and after the pulse is the front porch and the back porch, as it turns out. By playing with the front porch and back porch, you can move the VGA picture on the screen a little bit. And then after we get through the back porch, the VGA is back at pixel 0, 0, and we'll start doing the same thing again. I mentioned incidentally that the wastefulness here of this standard, the fact that we're spending lots of time not drawing anything to the screen, is an artifact of when we had to actually move the electron beam back to the left side of the screen or all the way back up to the top of the screen. Okay, so this is the standard that we're going to talk about the PIO implementation of, but I'm not going to get into that today with like 2 minutes remaining. I think we'll start there next time and talk through it in detail. Anything else people would like to discuss? Yes?
When we were showing the number of balls that had dropped to the bottom of the screen, in order to update that, we were like drawing a black rectangle and then redrawing the text.
Okay.
That was sort of leaving, it was like blinking as a result.
Yeah, I've seen this on a few. So another bug that you might see is for your text that you're writing, or perhaps for your histogram at the bottom, if you find that they are flashing, the flashing is a symptom of the fact, it's a symptom of you erasing and redrawing that big block of the VGA 30 times a second. It's something like the update rate of the VGA screen beating against the update rate of your pixels. The way to fix this is you only want to erase and redraw the pixels that change. And so, for instance, and you only want to redraw them when they actually do change. So let's say you have some text on the screen that says number of balls 5. Don't erase and redraw that 30 times a second because you don't have to. That's not changing. When you increase the balls to 6, then just erase the number 5 and replace it with a 6. And then don't erase it again until you change it. The histograms at the bottom, if you notice that they're flashing, it's probably because every frame you're erasing that whole rectangle that represents that particular bin of the histogram and redrawing it. From frame to frame, the heights of each of those rectangles are just moving probably a little bit. They go up a little bit, they go down a little bit. So if instead you only, let's say the rectangle grew, you just draw the new pixels on top of the old rectangle, instead of erasing the whole thing and redrawing the whole thing, it will eliminate the flashing. Or when the rectangle shrinks a little bit, you just erase the rows of that histogram bin that need to be erased, and you leave the rest unerased. That will eliminate the flashing. Some of you, your Galton board balls are flashing. That is a symptom of if your animation loop erases all the balls, then goes through and updates all the balls, and then redraws all the balls will flash. To fix that, what you do instead is erase a ball, update it, redraw it. Then go to the next ball. Erase it, update it, redraw it. Erase it, update it, redraw it. So that every ball is being erased and then redrawn, and then you erase this one and redraw it, and then you erase this one and redraw it. So individually, every ball is being updated 30 times a second, a little bit out of phase with one another, but that's perfectly okay. That completely eliminates the flashing. Any other strange artifacts folks are seeing? Okay, I'll be in lab this afternoon. I'll see many of you then, and I'll see the rest of you on Friday, if not before. No, tomorrow probably.